Hello, everyone. This is Will, and I am here with the 6th Advanced miniKanren Hangout. We talked for actually almost an hour now, or about an hour, about what to do and so forth. So I think that partly means we were just talking about various things related to miniKanren, but also we're maybe starting to run out of the ad hoc topics that we had plenty of because we hadn't done Hangouts for a while. So one of the questions is, what should we do for future Hangouts? One possibility would be to focus on just doing some hacking together on miniKanren and miniKanren related projects. Another would be to focus on things like program synthesis and Barliman, which is probably closer to my interest right now, because it does seem like we've made a lot of progress, and I kind of want to keep that up. So today, we've decided to try an experiment where Greg has made a lot of improvements to the relational interpreter used in Barliman. A lot of optimizations that have sped it up something like 7 orders of magnitude for some of the synthesis problems. However, the resulting interpreter is pretty complicated. And it turns out that, not surprisingly, a few of the optimizations get you most of the benefit, and most of the optimizations, are getting you relatively small benefit. So what we like to try now is an experiment in live coding. We're going to do it real time, see how it works. What we're going to try to do is take an interpreter that I had hacked on a couple weeks ago when I was in New York, based on conversations with Michael Ballantyne and a whole bunch of other people. Basically, we had this idea that we could sort of do some training on what scheme code looks like or closure code looks like or whatever, and try to see which patterns happen most often. So for example, one pattern that was very clear on the giant corpus of 46 scheme definitions I trained on was that inside of a lambda is usually an if or some conditional. Maybe a cond or whatever, but right now I'm sort of restricting it to if. So inside of a lambda is almost always a conditional, or it's a procedure application right away. So it's not calling a primitive, in other words, or it's not like a Boolean or something like that. So that sort of information, the fact that there's almost always an if inside of a lambda immediately inside of it, can be used to basically alter the search. And one way to do that that's easy is to just take the cond clauses and reorder them. So we can order the cond clauses by what is most likely to appear. If we can use a little context. So if we're inside a lambda, we keep track of which form we're inside of. If we're immediately inside of a lambda, then that cond clause for the interpreter, or the set of cond clause for the interpreter, is going to have if come earlier than it might otherwise. In fact, the default interpreter has if coming last because it has 3 recursive calls in it. So instead of having it come last, we want to have it come first or very close to first, and it gets more of the computational time. So I tried playing around with that, and it turns out that a whole bunch of the synthesis problems, like trying to synthesize something like append, become radically faster. I was able to get a number of orders of magnitude. I'm not even sure how many. However, it didn't seem to help very well with recursion. Recursion has always been quite tricky. So the idea is to try to take maybe the most useful optimization Greg has done, which is has to do with the apply line in the interpreter, a procedure application, and try to integrate that into the interpreter that I had written or hacked that uses the different cond orderings, and see if that hybrid interpreter does well with the synthesis of recursive programs like append. And so part of the idea is to try to have something simpler than full Barliman and something easier to hack, and also to start developing a methodology for applying these sorts of transformations to other programs we might have that we might want to speed up. And ultimately, maybe we'll be able to use something like dkanren, the language Greg's working on, to do these things. But for right now, I would just like to try to see what happens when we take peanut butter and chocolate and put them together and try to get a Reese's peanut butter cup or something like that. Two great things that go great together. That type of idea. So we're gonna try to do it live and see how it works. Okay. So let's see. We've got. So Greg is basically sending little snippets of code. All right. So Greg, we want to use project 0. Is that right? Okay. So I guess the first thing I need to do is I need to bring up the interpreters that I've written. Okay. So let me try to get that going. I tried hacking, by the way, the other day on these interpreters, testing a theory of Michael Ballantyne that trying to restrict the grammars actually doesn't make that big a difference, because with a regular conde, the clauses that come later are going to get so little time that it almost doesn't matter, and that seems to be the case. So let me just try to find this code in grams. All right, I'm going to put this code in the miniKanren Hangout summaries repo. So let me get this, get my code here, in grams for synthesis. I guess I may as well screen share here. Let me try screen sharing. Okay, so let's see if we can get the chat up. Chat going, yeah. All right. Okay, so chat is visible, by the way, on screen. So just fair warning. Let me try to get my repo. And let's see. So I want my ngrams repo. Here we go, ngrams for synthesis. And I'm bad at GitHub. You're about to see how bad I am. So I'm going to clone that into junk. Right. And then, okay. Okay, good. All right. So now what I'm going to do is in my new repo here, to, I guess, copy these things over. Hey, great. So I got all that. I get my faster MK and everything. I get my PMAS. Interp fastest. Yes, yes, yes. miniKanren. Okay. I think that's the code I need. All right. So let me just make sure I can load that and run it. Put one of these files. And test perp fastest.
By the way, do we have any miniKanren in Emacs Lisp?
You mean like a special mode for it or something?
No, I mean not G-Scheme, but Emacs Lisp.
Oh, like implemented in Emacs Lisp.
Yeah.
Oh, I don't know that anyone's implemented Emacs Lisp. They should be able to, because now Emacs Lisp supports lexical scope and all that. You should be able to do it pretty easily, I think. I haven't seen a version of that. I don't know if anyone's seen it. Like if we go to a miniKanren page, that would be a fun one. I hadn't even thought about that. Emacs. Well, if there is one, I haven't seen it. Emacs Lisp miniKanren.
Well, the miniKanren mode for Emacs had better be implemented in miniKanren, right?
Well, I yeah.
The performance would be great.
I'm sure it would be great. So what is micro Lisp? Micro logic. Oh, it's closure. Okay, never mind. In fact, I knew about this implementation. Okay, so here I am running the tests. Test interp fastest. Okay, so these are the tests, and I guess part of the thing that makes this a little challenging is, just testing the synthesis stuff, right? Is a little tricky. And Greg, I don't know sort of what techniques you usually use to try to know if you're making progress. It can be a little bit difficult to tell, because sometimes you'll make a change, of course, and it will speed up some tests and slow down others. I think it has been the case that the tests having to do with recursions or arguments in recursions have not run quickly. So here's the test, Maptxt. That's pretty slow. So I think you can see that we're trying to do a test where we're trying to synthesize part of map. Okay, so here's map, and we have 3 tests for map. Or sorry, 4 tests for map. And we're trying to synthesize, actually, we're trying to synthesize recursion here also. Oh, no, sorry, here's the recursion. Okay, so notice that we're not synthesizing anything in the recursion. Well, we can synthesize actually most of the rest of it. We don't have to have a whole lot of structure. It takes 25 seconds to synthesize that. As soon as we start going into the recursions, my experience has been like things get much nastier. So that's been a little tricky. So if I look at the append tests, let's see if I have any of these that try to get into the recursive arguments. Yeah, so here we have some, like append 8. Append 8, what's the difference between append 8 and append 9? Append 8 is trying to synthesize the first argument to append. Let's see how fast that is. Oh, we haven't even gotten to that one yet, I guess. Is that right? Is that after? Yeah, okay, that's after map. Okay, so at some point we'll start getting into this. Okay, you can see this that the maps start getting quite slow, right? So what does map 17 look like? Yeah, so we're not even doing any recursions, and this already takes 75 seconds. We're not trying any of the arguments in the recursion position. We're not trying, so. For a comparison, Barliman can synthesize all of append in, I don't know, like under 10 seconds or something, or under 15 seconds from some carefully chosen example. They're reasonable examples, but you do have to be a little careful with like the ordering of the examples and so forth. And here, maybe my examples aren't very good. Maybe I could have done a lot better with my examples. I don't know, but I tried not to get into a state where I was like really trying to be very specific with my examples. One thing I will say that's probably hurting me here is I'm not using the gensim tricks. So, we use a trick where we use absento constraints to try to basically pretend, or to sort of act like a Lexley scope gensim. So I'm actually not doing that. Am I using it anywhere? These are just the closure constraints. Okay, so yeah, here we go. So like here in append 21, this is the sort of trick we play in Barliman, where we have these absento constraints, so that as we're using lists containing the symbol B, the symbol D, and E, we say that those cannot contain or cannot be contained within the code that we're trying to synthesize, for example. Although here, this constraint's kind of on R instead of Q, so this is a little awkward. This isn't really right. So I don't think that's actually not a very good use of the absento constraints. I guess I did that reactively based on what it was specializing or whatever. But anyway, so if you really want to make the synthesis faster, you can use this absento trick to try to speed things up. Let's see how we're doing our tests here. Oh, we're still on map. Is map 19 the last one? It is the last one. Okay, so hopefully that'll come back. And even from map, okay, so map 19, we actually try to do something here with the recursive call. And so that's actually a pretty decent amount of synthesis. I mean, we still have a fair amount of structure, but we have a lot of variables there, and we're not using the absento trick. So, and these tests aren't super carefully chosen, I don't think. But it also takes a long time, right? I mean, the last one took 75 seconds, and I think this is going to take 5 minutes or something. So I'll just leave that running in the background, but you can see append, and remember, we can synthesize all of append if we use the absento trick correctly in Barliman within a few seconds. And I think I don't think I was able to synthesize anything really within the recursive call of interest. Let's see if we've got any more. Okay, well, actually, does that one actually come back? If so, that's actually pretty good. I don't know if that actually comes back or how long it takes. So we'll just, I think what I'll do actually is kill this. And then I'll save that transcript as fastest benchmark for map.txt. Okay, so that we have those timings. And let me for right now comment out all of the map tests, and then let's just try to see how the appends do. I don't even know if that 19 one comes back anytime soon, so I'll comment those out. Hopefully this will give us some baseline for what we want to do. Now, I will say that, I've seen significant differences in the benchmarks based on how much work the CPU is doing and how hot it's running and stuff like that. So, wait. This is nonsense. I don't believe this for a second. Append 19E is coming back in a... Really? Let's try that. That's true. This is working much better than I thought, but I don't remember it coming back this well. Okay, so here's our append example, and you can see that we have, not much going on there. Huh. 165 milliseconds. All right, well, maybe we're doing better than I thought. Okay, let me look at the other tests and see how aggressive we get. Huh. Well, that actually doesn't seem so bad, does it? Okay, so maybe, all right, so let me try another test here. Now we still are giving a fair amount of structure. We're saying how many arguments there are. We've got the if right here. We're saying that it's an append and so forth. So that stuff is still significant. And these absentos, though, are not really set up correctly. So these are kind of stupid. Okay. Okay, so let me just try creating another test. So I'll call this 19F. And so the first thing is I notice these absentos kind of aren't right because they're only on part of the code. So to really do this right, I think what we want to do is we want to say that the code is going to be this thing. We'll call that code. Okay. Call that code. And then inside of that, we can have a fresh, I guess. See if I do anything really stupid here. If I do, let me know. Okay, and now I'm going to say these constraints are actually on code, not on R. So, okay, so we don't want A, B, C, D, E, or F appearing in code. Okay, that looks right. And we get called lists. Great. And these are supposedly the outputs. So notice I'm careful here to use dots for the answers. So here I'm being a little careful with the answers. I'm not actually giving lists here. I'm trying to keep things short to help with the synthesis. So let's see what I get back and how well that works. Okay, 120 milliseconds, and what do I get back? Yeah, that looks right. Okay. 120 milliseconds for that. And, I believe that's like way better than the default behavior if you don't have any reordering. So I wasn't able to get anything close to that, I don't think. What I really should do then is go back and try to, run exactly the same tests on the original version. Because I don't really even know how much. Uh-oh, my Emacs crashed. All right. Get my Emacs again. Okay, so Greg says under 10 seconds for reasonable examples and under 2 seconds for the really clever examples. And that's without saying how many arguments, is that right? Or do you have to say how many arguments for that? Okay. Straps again. Here's my 19F. Okay, so that came back in 114 milliseconds. Okay. So now, basically, we're just trying to see how many variables we can put in where and still perform decently. So here's G. So we still aren't very slow. All right, so now I'm going to get a little more aggressive. So I'm going to replace all of this with U. That whole thing is going to be U now. So I've removed a little of the structure on one of the recursive arguments. So let's see how this does. Wow, so you can see the difference there. So, before it was 112 milliseconds or something, and now just removing the fact that it had to be an application seems to be really slowing it down. Okay, so 2 seconds, you can synthesize all of append in 2 seconds without even giving the number of arguments. If you choose your examples carefully. So here, I don't know, maybe my examples could be somewhat better, but the point is, just saying that this first argument to append had to be an application, sped it up orders of magnitude. Now it seems too slow to even come back. So is u.v. Yeah, wow. So look at that, 100 milliseconds versus, I let it run for 15 seconds or something and didn't come back. So this, I think, gives you some sense of what it's like when you're dealing with these recursive arguments. You can have a lot less structure in other parts of the code, but if you start messing with the recursions, you suddenly fall off a cliff. And so here, actually, I'm just curious to see how we do, say, null s, cons carvel. That's really fast, 30 milliseconds. Everything's instantiated except the recursive calls. What happens if I do this now? All right, so you can see that as soon as we start messing around with that first recursive call, we're really in trouble. It's just not coming back anytime soon. And I think I've let this run for minutes and it doesn't come back. So, the recursion is really the critical part. And so that's supposed to be could or vel. And so it just kind of falls off a cliff, where before it was 30 milliseconds, and then you remove a little bit of structure, and now suddenly it's super slow. And it's not clear to me why it's super slow, because when we just said it was an application, that made it fast. That does make me wonder, by the way, that maybe, so why is it so slow, whereas before it was so fast? So if we look at the the interp fastest, let's look at the default ordering for the interpreter, because maybe that gives us a hint. Let's see if I can find it. Okay. Here's the if ordering. So we got all these different orderings. Okay, so here is the default ordering for the interpreter, and that recursive case is just using the default. It's not doing anything special. So why is it the case that it's so important to make it look like it's a procedure, or to say it's a pair? Well, the only thing expensive that's not a pair that I can see is going to be lookup. Isn't that the only thing that's saying it has to be a pair is going to rule out?
Did you do a dotted pair, or did you do a list of two things?
I thought I was able to do a dotted pair. Let me try to go back. Okay, so this thing takes too long, right? Let me go back. If I do uv, that's list2. Okay, that's 29 milliseconds. If I do u dot v, that's 33 milliseconds. So there's almost no structure there. It's ruling out that it's a a Boolean. It can't be an atomic value, right? So it can't be a Boolean, it can't be a variable lookup, and it can't be a number. Why is that making such a huge difference? Is, I guess, the question. And so let me see if I put an S in there. So I'm really very instantiated here, right? Except for everything's instantiated except for that argument, and it's fast. Okay, so now it comes back. It comes back actually pretty quickly, 53 milliseconds. So this is something I just don't understand. Why is it that we fall off a cliff as soon as they're both logic variables? Anyone have an idea? That just seems bizarre to me. Doesn't that seem strange? That we can go back, we went back to one case where almost everything, where there was just like a ton of variables everywhere, like in this case, right? Now, okay, so here it's going to be slow, right? Here it's too slow. But even here, if you just do u.v, it's fine.
Can you propose such a pair, Greg, that would get rewards quickly?
All right, so Greg thinks there might be pairs of variable combinations for u and v that get rewards really quickly, even if they don't pan out for the whole thing. Yeah, so this is why I was hoping that taking one of the optimizations from Barliman might help, right? Because there's obviously something going on here with the recursion, because I can put variables all over the rest of the place and it doesn't hurt it, not really. But if I put a variable here, then unless this variable is also instantiated, then we're in trouble. So there's something very special about this sort of complex recursive argument position. And I also thought maybe this is something where if we just train on what scheme programs look like or whatever, and we actually include that in the sort of bigrams model of Kandi reordering, that maybe we could do better with the recursion somehow. I don't know. Someone posted that. So that's sort of the big mystery to me, and this is behavior I've noticed for a long time. But in this case, it's actually just really dramatic because the rest of the code is actually pretty fast for synthesis through some of these other optimizations. So what is it about this position or that recursion that makes it so slow?
Can you try adding absentos to U that rule out cases from the interpreter and see if that makes it faster? I guess we're only allowed symbol absentos, but you could put, and we're trying to rule out atomic things. What if you did like absento S from U? Does that have any effect? So you're saying it can't be a reference to the variable S. Can't be a reference to the wrong list.
Like, The symbol S, you mean?
Yeah.
You?
Yep.
Okay. Our situation has not improved, but I see where you're going. So we could also put, well, L and S are the only thing other than append. I could put append in there, I guess. We can't put an L in there since it actually uses an L. Okay. And what if we kind of play this game with V as well? So we could say L doesn't appear in V. And we could say append doesn't appear in V like that. Doesn't seem to help.
So it could be.
No. Well, it did come back.
Yes, slowly.
Well, yeah, but it seemed to help at least some. But it wasn't instantaneous for sure. All right, so it does help some. Well, okay, so the other thing we could do, I guess, would... Well, so I guess the problem is, like, you don't want to make the variable case, like, come really low, right? Because it is likely to be a variable reference. But maybe you could say, maybe it's less likely to be another recursive call if it's immediately within a recursive call or something like that. I don't know if that's what it's trying to do. I mean, I can imagine if it's trying a recursive call inside the recursive call, maybe that's making it slow. Part of it may be just trying to print out, what it's generating for U's and V's to see what it thinks, they should be.
Sure, I mean, you could give it a try.
All right. That. We did learn something by doing it with some other code. Okay, so let's see. What's the best way to do it? I guess. Do we still want to keep maybe one of the calls? Or maybe we have the calls and don't say what the answer is. Maybe that's a variable. I'm not sure what the best way to set that up is.
The really weird thing with this one is that it's what you're being rewarded for doing is ruling out simple expressions. It's not like you're being rewarded for ruling out complex expressions and being like, well, it has to be a symbol or a number. It's that you're ruling out the simplest things, which are either kind of constants or their lookup. And it seems like the problem really has to be with the lookup case, because there are finitely many constant cases, and they're very small, right?
Yeah, it seems like it has to be lookup because the reason it seems like it has to be lookup is that when I make this a pair, right, then it speeds it up a whole lot.
Yeah, and so let's see.
And lookup seems like the only thing that's going to be slow potentially. It might be rewarding unimportant internal successes from something like eval listo on the operands.
My other question, Greg, is whether like the first result coming out of lookup-o can end up rewarded in a way that other possibilities can't overtake because of associativity issues. So that's something I'm going to try and draw a diagram and see if it's true.
Okay, here's my lookup-o. seems pretty vanilla. We do have the recursive versus the closure case. So where's the rec being used here?
And just to confirm that your implementation of car correctly has an absento closure.
And let's see about the absento closure. Quote has one. Maybe quote's the only thing that has it.
Because don't we need to prevent car from pulling apart closures?
Well, there's a way to test that. Let's. I mean, the safest way is to put the absento across the entire eval. But I think that
Sure.
that might be slow. But let's see if we can get it to generate.
I'm just trying to test a hypothesis that maybe what's happening is that lookup is producing a closure, and that can get some way through the recursive call to appendo because car works on it.
Well, let's see. Okay, so here's a closure. So how do we want to do this? We want to run this backwards, right? We want to see what expressions will generate closure. They should all be equivalent to the identity function.
I'm not sure that's what you want. I think it's just you want to try applying car to lambda XX.
Let's see if we can do this. Oh, whoops. Car of lambda XX.
Yeah, just try running that for it.
Computer says no.
Well, that's good, but why? How does it? What makes it say no?
Oh, I think I may have. That's a good question. Let's take a look. There's an absento case in car.
Yeah, that's what we're expecting. I just was asking if it was actually there. There may be a disequality in car.
Well, maybe there's one down lower for the prim case.
Can we just
quote?
Look at the car case?
Well, there's not one car case anymore, maybe. I'm not sure. There might be one car case.
So
prim.car. Oh, there's a disquality constraint.
okay, that's what does it. Cool, thanks.
Okay. So that doesn't seem to be the problem. Now the So let's see. What was I was trying to do? I was trying to see what was going to be filled in here for U and V, right? By default. Why isn't that not? Why isn't that coming back? Oh, interesting. So this may not be an easier synthesis problem. All right, here we go. Because I've given it so much structure, I guess it actually has to do the actual synthesis to get it back. And I'm confused there. I wonder if there's an infinite loop that gets rewarded after getting ahead. It will use most of the resources. Well, this one doesn't make sense to me. Like 5. That's fine, but why? Oh. Do you see this example? Why in the world isn't this coming back right away? I'm saying it can be called with any arguments, and it can return any value. And yet it's taking, it's taken what, 15 seconds at least?
Is it just diverging?
It might be, or taking a really long time. But I mean, the thing is, if I just put in the u.v, it's exactly the same program. It comes back instantly. So if I just replace that with a u, so this problem seems just as hard as synthesis, even though I'm calling it on logic variables, and I can say it can have any value, which I find kind of strange. Why would that be the case?
Does it help if you instantiate W? I'm sure it does, but just check.
It does, but it's still not very fast.
Yeah, that's remarkably slow.
It is, given that if I do u.v, it's going to come back right away. Yeah.
Well, you found us a good mystery. It's the kind of mystery we'll probably learn something if we figure it out.
Yep. Okay, let me save that one for posterity.
Could you actually like email that to me, or?
Yeah.
Yeah. That'd be a good one to ponder.
I can do better than that. I can check it in.
Does that one thoroughly puzzle you as well, Greg? Seems really weird that we'd be being slow when we don't have to satisfy anything, really.
Okay. It's checked in. You should be able to grab it and run it. Yeah, that is mysterious. Oh, you noticed a bug. Okay. We have to... Are you talking about dealing with Absento or something else?
Oh, that's fun.
Okay. So what do I need to do?
Just like that disequal closure val, put another one disequal prim val.
Disequal prim val.
On just the same lines as the disequal closure val has. Just like in
Right
that
here?
same fresh, add a disequal prim val.
What is prim val? I don't remember what a prim val is.
Well, no, disequal prim to val, and prim is the tag for primitives in the environment. Primitive values. So you look up car, and it gives you a prim object.
So what if you wanted to return the value of car? Like, why isn't that allowed? Isn't that allowed?
You're just not allowed to take car, the car of car, right? You're allowed to take the car of cons.
Oh, I see.
Car.
So I see. So you can't take the car of.
Yep. And this is why these
car.
are disequalities instead of absentos.
Okay.
And you need to do that on cooter as well, which is just below.
Right there.
Yep.
Okay. And anywhere else?
Unless you've duplicated any of this code.
I don't think so. I think for the primitives that. Well, maybe not.
You can search for disequal closure.
Yeah.
Disequal to closure, that line.
Uh-oh. 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 Yeah, there might be a couple. There's one. Oh, copy and paste, so bad. We need to figure out some abstraction for this stuff. We also need to change faster interp then in faster MK. Because I took this code from the full interp, in faster MK. That's where I took it from. So that's wrong.
I don't believe that has this bug. It's not quite as bad of a bug as the closure one would be, just because. Oh wait, do we have to make sure you can't cons prim with stuff, or we absento it from quotes, so that should be safe, right? Because then there's no way to get the prim.
Do we?
Yeah, I'm pretty sure we have an absento.
Oh, yeah.
Yep.
Yeah. Okay. All right. So you think that solves that problem?
Yeah. So we should be safe for consing. It's just the
All
cons
right.
and cutters.
Well, let's reload it. Now I'm excited to see how fast everything's going to run.
Is there a pattern matcher in this version that you're using?
Yep.
There is?
Yep.
Okay, there's disequalities for closures in the pattern matcher. You need to make sure those have disequalities for pim as well. Just anywhere there's a disequality with closure, there also needs to be one with pim.
for literal low. That. Well. All right.
Yep. Any disquality with closure needs one with pretty sure. That one.
Yeah, May will speed things up. That's right. That's what I'm hoping. Let's see. This is all going to run blazingly fast now. Okay, so Greg, good question. Does Barliman have that error as well? Sure does. Okay. Oh no, that's right, because I added those things now. Oh, 19G, your friend. It's not doing so well. We're seeing basically the same behavior.
Does that slow one at the top there?
I'm sure because I didn't put a time around it, and if you noticed, like it took a few seconds to start printing anything.
Is it slow? It appears slow. Yes. Yeah. Because that one should be instant, right? If everything was good in the world, it would be instant.
Right. The other one. Oh. Huh? Wait, did I not? Let's do the first one. Wait, what happened?
Did that get slower?
That was a fast one. Now I reconstructed that by hand, so maybe I just screwed it up. Go back down here. Okay. And S back. Okay. That was W. That's fast. And if I make this U, so. All right. Let me make sure I've got all my tests in place because I don't want to lose the things we were doing. This one took what, like 6 seconds before? I wonder if those absentos slowed things down. No one used to come back, right?
Correctness.
Yeah, who wants correctness? That's right. Okay. All right, so great test name. And this is going to be VW. This one should be fast, presumably. Oh yeah, I have to say what it's going to return. Yeah, I guess the bottom line is we don't really understand why it's slow, right? And so if we don't really understand why it's slow, it's going to be hard to know why it's hard to speed it up. This one should be fast. Yep. And the other one, I assume, won't come back anytime soon. Or maybe it'll come back after 10 or 20 seconds or something. But that's the one that actually came back before, though. So what's going on? Did those appendos slow it down too much? I mean, if so, I think we just have to wait a little while. Our situation has not improved. All right. So So let's see, I can do, was it get? It's not coming back anytime soon. So what I want to do, I think, is get add terp fastest fixed. And commit. Okay. And I'll add the tests. Okay. And then I'm going to check out, I'm going to go back to the old version.
So I'm looking at that example that's at the top of the test there that's slow.
Yeah.
And I'm thinking about kind of what's happening with evaluating it. And one of the things to think about is that in this case, it's guessing and checking on X and Y.
Okay.
So when you provide a fully uninstantiated append call, right, it ends up totally guessing and checking on X and Y. And since there are two things to guess and check on, it just may be unlikely to find a combination that's going to work. So like any individual argument, sure, but it has to guess both of them and get them both correct before the check will pass, right?
All right. So maybe that's...
So that would be something that would be easily fixed by the optimization that we're proposing to apply today.
Yeah. So then it will delay it until...
Yeah. So I guess my question is for Greg, does that explanation of why that particular run is slow make sense to you?
Huh. Maybe I screwed up that other test. So there was that one thing that took like 6 seconds to run, right? With the absentos. Doesn't seem to be coming back even with the unfixed version of things. Ah, okay, that's the test. All right, so how is this different from what I had before? Oh, I think you're right. I think you're right, because look at this example. Look at these two tests. They should be identical, except that the one on the left actually says what the outputs are, whereas the one on the right shows a val. And so the one on the right, well, you might think it's easier in some sense, but it's actually much harder because it can't fail. Yeah, okay. All right, so I take it back. I think the fixes we made didn't slow anything down. I will try it again in a second. Yeah, having this val thing is having these fresh variables does not necessarily help her, I guess. All right. Much better to have the outputs. Okay. So it should be the same.
All right, I think I have a theory for why adding the u.v sort of thing helps so much.
Okay.
So let's think about what happens when we don't have the u.v.
Okay.
So we're going to call first, so the recursion there is first going to recur on u, then on v, right?
Okay, so let's look at an example. Which test should I look at?
The one with both
19.
u and v being variables. So the s there not being constant, I don't know. Not the one at the top there.
Like this one.
Yeah, that one. Sure.
Okay. 19G.
Yep.
The hard test. Or that one. Okay. I don't know what to call it. Okay, anyway. Yeah, that one. Yep.
Yeah. All right, so if we think about what is in the default ordering early, number is early, but that's basically free because there's only one possibility there, right?
Yep.
There's nothing interesting with that, so really it's just got to be the lookup case, right? That would matter.
It would seem like. That's the
I
only
guess
thing.
there's booleans too, but who cares? So it's probably the lookup case. So if we think about what's going to happen there, it's going to first evaluate u, right?
Yep.
And it's going to hit the lookup case, and it's going to choose something, and that successfully looks up, right?
Okay.
And so then the next,
it's going to get stuck on that.
yeah, so it's going to choose that thing, and that's at the front for now, right? It succeeded, right? So now half the time is being spent on that possibility with all the possibilities for v.
So in other words, if u and v were swapped, it would be okay. Is that right? Because v is supposed to be a symbol or variable.
It would be okay-ish. I mean, I guess it would be okay because L and S are in fact at the top of the environment.
Mm-hmm.
If V was meant to be picking something that's deeper in the environment, then it could still be expensive.
Yeah.
But given that S is something that's right at the top of the environment, it's going to get to that pretty quick. But as it is, what's going to happen is before it checks anything, right, it's just going to try for each of these environment entries, it's going to try all values of V, and there are infinitely many values of V, right?
Yep.
And so that basically means that the symbol case is not going to go away. It's not going to fail, right?
Mm-hmm.
So the symbol case of the interpreter is going to sit there trying all of these symbols and taking up, so the quote case failed, so the number case failed. So now we go into the symbolo case.
So the basic problem is that the two arguments to append do not sort of get equal time. They're not like sufficiently. I mean, U gets picked, and then V goes through a zillion permutations, and and the initial picks for U are all just variables are bound in the environment, and for each one of those, there are infinitely many V's. And so U is basically getting stuck in the variable lookup case. But you could easily get stuck, I guess, just as well in some other case, right?
Oh, am I wrong about the value used for arguments? Okay, I didn't realize that, but sure. So symbols first, right? and that's what matters here.
Although the interesting thing is that as soon as you give it any structure, it's really fast. Even though even though call to Kotaro isn't the first possible answer. So maybe variable lookup is particularly bad as opposed to other operations. Is that true? Is there some reason to think that variable lookup would be worse than?
There's a lot of ways to do variable lookup. Yeah, I got to think about this. I will ponder and come back to it.
I mean, in some sense, there aren't that many variables in the environment bound, right? Well, I guess our initial environment has a fair number now. So I guess there are probably like 20 things in the environment that it can, for each one of those. Are you getting the exponential drop off with the variable lookups where like, the last variable case is like 1 in 2 to the 20th of the computation time or something like that?
You maybe. I've got to think about that again.
If you get that, then yeah, I could see how you could get into trouble.
Yeah.
And I guess that would be consistent with how ruling out some of the cases for U and V help. So if that's true, then if we ruled out other cases, like rule
out all of the environment entries for you.
Yeah, that's what I was gonna say. If you rule out the environment entries, then it should be like much faster, right?
Yep.
All right. Let me try that. That's so stupid. Let's try it. All right. So like null.
Cons, car.
Yeah. Now that seems a little cheating, but sure.
Well, I mean, it's obviously
it should be disequality. It should be disequality, not absento.
Correct.
That would be fair, right? That's a lot more fair. So null, car, cutter. Okay, and if that is true, then I guess one question is what, are there other approaches then we can use to kind of combat that problem? List. I don't know. Let's start with that, I guess.
Well, Greg's optimization certainly helps here, right? But
yeah, but I guess what I'm saying is that shouldn't be, there should be other ways to do it then, right?
To do what?
Presumably there'll be other ways to not get into this trouble.
Not necessarily.
Why not? There should be a bunch of ways to do it, probably.
Well, I mean, fundamentally, the problem is that we do like when we have a conjunction saying, run with that first one, give it a lot of time, right?
Well, maybe that's a problem. Maybe we need to try a somewhat different search.
I guess what I'm saying is that search gives us lots of benefits elsewhere. So maybe we can special case this particular scenario with environment lookup or something, but that seems to be an advantage. If you turn off that behavior, bad things happen.
Well, it seems that it helps a lot to comment these things out. I don't comment those. If I only comment out S and append for you, it takes 12 seconds. Comment them all out, all those, then it's 200 some milliseconds. So
wait, I'm confused. What do you mean by comment out?
Can you see my screen?
Yeah. So having more of those.
Having more of those makes it. Yeah. Having more of these disquality constraints radically speeds it up.
Okay, good. Each one. Okay, is there anywhere close to like a factor of 2 for each one?
Well, let's see. That was 278. This is 4. Yeah, that's about a factor of 2 there. Let me just try another one. roughly a
Okay,
factor
what
of
if we
2.
do 2? 2 of them commented. Yep. All right, so we can sort of
Seems to
see
be our
what's happening. That
problem.
things are getting nested.
Yeah. Okay. That's an important safety tip. So U is getting stuck on that variable lookup line. Well, so it's the combination of U and V. If it were just U, it'd be fine, right?
Correct.
The problem is we're doing
because it
left to
could-
right evaluation.
It could eliminate each possibility quickly, right?
The problem is that U has to be chosen before V. Yeah.
Is that we choose U, and then there are infinitely many values that can cause V to succeed before we test by applying the overall append.
Okay.
So that means that we can never stop considering any of these environment entries. We always are going to continue considering them because there could be some V that we just haven't discovered yet that they will work together with. So part of the problem is that we are unable to notice in this particular model that the reason why this choice of U is failing is independent of the choice of V.
Yeah.
And that's something that if you push the evaluation of the body forward, then you get some of that because you find out that you've already got the body. So as you're considering these choices of U, then they fail. The reason that they fail is immediately apparent, and you don't have to notice later that it's not for good reason.
Okay, so anyway, the point of doing this whole exercise was to try to understand where sort of the naive version wasn't doing well. And I think we have a better idea now. And further, if I do interpret faster, fastest fixed, okay. I see. Okay, so it's got those subcentos. Alrighty. Well, having learned all that, yeah, giving you a lot of the ideas for the debugger. Yeah, debugger would be great.
So what we've learned is that Greg's optimization should help a lot if we implement it.
Yeah. Okay. So that's good. So why don't the other parts of the synthesis problem get stuck like that? Why is it just the recursive arguments?
Well, where else would get stuck? So the key here is that I evaluate something and I can't immediately check whether it's any good.
Okay.
And the recursion is the only place where that's the case.
Was that really true? I mean, look. With stuff like that. Is that true that there's only, you can immediately reject anything for Q, R, S, and T?
So S ends up being something like cons, right? I guess we could consider it being an application.
I mean, it is an application, right?
Yeah. Well, but the question is whether it's a primitive application or a non-primitive, because they behave differently, right? Primitives end up being able to cut off more quickly. But yes, there for S, we will consider values of S that are environment lookups.
So okay, that's an interesting point. Why do primitives cut off more quickly?
Because we always evaluate the effect of the primitive before we evaluate the argument, because primitives can never diverge. The evaluation of the body of a primitive can't diverge. So there's an obvious ordering. You always, for the car or whatever, you'll always do the connection of the output to the argument to the primitive before you evaluate the argument.
Okay. Now, S could be some arbitrary lambda expression, right?
Yes.
Or a let rec or something. I guess that's where ordering a variable, or ordering the Kandi clauses can help.
Well, it could be append, right?
Yeah, could be append, absolutely.
So let's say it was
so
append.
why, so if that's append, right, then, okay, by that theory, if I made S fresh, would that cause a problem then? Because T and S could be anything? You see what I'm saying?
Let me think a little more.
Will that get us into sort of the same state?
All right, so let's say I don't pick append. Well, so anything that's not append in the environment is going to be a list, which is illegitimate in that position, or it's going to be a primitive, right?
For what? For S or for T?
For S. I'm thinking about for S first, right?
Okay, S is either going to...
We've either got L or S, which are lists. We've got primitives, or we've got the recursive function append. And that's all that's in our environment right now.
That I believe is true.
So for primitives, if we consider a primitive, well, first we have to match the arity, but say we've matched the arity. So it could be cons or car or coulda or whatever, right?
Yep.
We pick one of those things. Now when we're guessing T, we have a connection to the output available through that primitive. So we're not blindly guessing T in that case. Does that make sense?
Okay.
If S happens to be chosen as append, then we are blindly guessing T, but we're only blindly guessing one variable.
Okay, so that's what I was asking. If this S here were to become fresh, do you think we would see the performance that we just said?
So let me think a little bit more. So in that case, so we're assuming S was append. Now we blindly guess T, and then we try and evaluate the recursion. To evaluate the recursion, we do the car of L, and then we have to blindly guess S, and then so our blind guess of S, there are infinitely many values, and that will just end up unified with the output of append, more or less, right, after a few steps of append processing. So yeah, I think if you put a logic variable in that position, bad things would happen.
All right, let's try it. So I will uninstantiate everything else. Okay. So that was 61 milliseconds.
Okay.
All right. And now, 2 there. 70 milliseconds. Came back just fine.
It's not a predictive science yet. Bummer. Or at least I'm not intelligent enough for it to be.
Well, wait, hold on. It gave us kind of a nonsense answer. Hold on. Oh no, those answers aren't necessarily nonsense. What I should do what I did before, where I had
The code thing. Yeah.
Yeah.
Oh, I guess I can post talk. I can explain why this happened. Maybe.
Okay.
So the first choice, there's only one bad option, right? If we look up for S, right, only one of the choices for S is going to give us bad behavior.
Okay.
So that's only getting 50% of the time.
Right.
And there are other good choices of S that mean that we can make progress, so they still have a chance. So if you, I mean, I guess there would be no way for it to pass, but if you forced S to be append, right, then we would see interesting behavior.
This S?
Yeah, but then that wouldn't satisfy your tests, right? So, I mean, we expect this to fail because a program of that structure isn't going to pass the tests.
Yeah.
So that's not surprising.
So what if I do like UV? Does that matter?
No, because the point is that S is going to try something other than append quite quickly. And so when it finds the other thing, that is going to end up not being too expensive.
Okay. All right. So do we think the only way to solve it is with Greg's reordering trick?
I don't know. I haven't drawn the diagrams yet, so I'm not sure.
All right.
How to draw search tree diagrams and think hard. But I think the most direct way to solve it would be to use Greg's optimization.
Well, we'll try that. Okay, so let's now first, wait, hold on. I do have one question here. So for the fixed one, computed, oh. Oh, yeah, I guess we did give it a lot of free space. All right. Okay, so I guess we need to go ahead and add Greg's stuff, right?
Oh, and Greg's got to run it. Just a moment.
Okay. Greg's got to run. So do you know how to do it?
No, he said he'll be right back. So
Oh, okay.
shouldn't be a problem. I'm sure I could decode his code, but having him help would probably be easier.
Yeah, this is the one that's too slow. Alrighty. Yeah, now the tests have changed because we have these absentos. Absento. Wait, what? Oh, it's not. Oh, yeah. Sure. Looks like those all pass now.
This might be a situation where if we don't have Greg's optimization, we want a different implementation of bind, maybe.
Okay.
Because really, if you've got, well, I don't know. In this case, what I'm going to say is true. In general, maybe it's not. But in this case, your traces of U and V, they aren't really validated at all until I've gotten the body to go. So just because I have something that succeeded with U, right? That's like big whoop, right? I don't really care.
Yeah.
And succeeded with U and V, still nothing special, right?
Sure.
But right now the search rewards exorbitantly succeeding with U and V. To the extent that other possibilities get cut out. So one choice would be to say, well, maybe we shouldn't do that. Maybe we should only reward after you've actually ran the body of append.
So what if we said something like, we're in the context of a recursive call now, because we can tell that, right?
Yeah.
And we're switching now to breadth first search or something like that.
But I don't think that would work if the arguments, if U was something that was more complicated to get to succeed, right? If U was some sub-expression and you were having to, had some other behavior on it that made it harder to get it to actually even evaluate that sub-expression because you were like choosing parts of it that were logic variables instead of the whole thing.
I'm not sure I know what you mean by that.
Okay, so right now it's absolutely trivial to find the U that will successfully evaluate, right?
Well, it's coder of L, so it's not absolutely trivial because V is absolutely
sorry, no. I'm saying to find a U that on its own, the recursive evaluate call will succeed, right? Regardless of the other evaluate calls. Do you agree? So I can pick any U that is a valid scheme expression.
Yeah.
And it is unconstrained until I get to the point where I evaluate the body of append in the recursion.
That's true. Yep, I agree with that.
So for that initial place, right? And right now we're rewarding success there, but it's really easy to succeed, so we shouldn't really be rewarding it, right?
All right.
But what if U was replaced by a complex sub-expression with holes, where it was in fact difficult to make that succeed?
Okay.
then we would want to reward making that succeed. Because we would be rewarding sort of a narrowing of the space, right?
Well, what would it mean to succeed? Just produce a value?
Yeah.
I guess it depends how complicated it is.
Yeah, I guess is it possible to even construct something? Well, so we could construct something in there that how do we how could we do something that would be difficult to fill? Would it be possible at all?
Well, I was thinking this is a place where types would actually help, right? Because if you know the type of L is a list, then U can't just be anything.
Well, so the optimization we're about to do is going to solve that problem by pushing that information back anyway.
I understand that, but I would like, it's always good to be able to solve a problem many ways, right?
Sure. We're just going to do the dynamic equivalent of that by propagating the information that we've done null and car.
But I do suspect if you had types on this, then if you had a type for U, that U has to evaluate to something that's a list, that you might do pretty well.
Yeah, I mean, that would throw out everything in the environment except for LNS.
Yeah.
Right? So that would certainly help.
Well, things involving LNS, right?
Yeah, but well, it would throw out every simple variable reference other than LNS, right?
Yeah.
And we found that if we throw out all the simple variable references and say, u.v in there, right? Yeah. That makes things fast.
That's right. I agree with that. Okay. I think I ran my test now. Okay, all my tests are now good. Great. All right, well, I think I'm ready to make these changes. So I've got the fixed interpreter now.
So can I just ask a quick question? Is there a case where a scheme expression with uninstantiated return value, where it is difficult to fill in the arguments such that it evaluates to something? Well, I guess that append call was an example.
What were you saying?
I'm saying, is there a situation where if we have a scheme expression, the return value is uninstantiated, is it ever difficult to fill in the holes to make it evaluate to some value, but it's not specified what value?
Well, is the scheme expression... I mean, how much structure does the scheme expression have, or what's the context of it? I mean, so the thing that makes sense in hindsight is when I was doing these tests and I was replacing these outputs with like var, or sorry, val or some logic variable, it actually slowed things down a lot because then it couldn't like fail quickly, right? And so it turned out that it seemed like it was just as hard, or it was harder than doing a synthesis problem, even though it had logic variables all over the place in the inputs to append and the output. So it seems like if you have this amount of structure for the context of those variables, that it actually can be quite difficult to produce any value at all, is my guess. That's what seemed to be happening in those tests, as if I understand it. I mean, I guess, it was this sort of thing, right?
Yeah.
XY val. And I thought, well, that would be really easy. It's like, no, it's not. It's not easy.
I wonder if there's some way to measure like how much work miniKanren's done. And only kind of reward based on how much work it's done. Like we have some measure of work, like satisfying conjuncts, right?
Yeah.
But sometimes satisfying a conjunct is a whole lot easier than than other situations. So maybe more tests in more detail.
Okay, that's an interesting idea. So I guess here's one way, and this reminds me a little of miniKanren. What if you tried this? Like, what if when you find a successful answer, you say, well, hold on a second. Let me try some other choices first and do a little bit of work along all the choices. And if it turns out that like you can trivially find a solution among many different paths, that probably tells you don't want to commit fully to the first one you found.
Yeah, or another way to phrase that would be just to say, okay, well, you are rewarded based on the number of failures that were required to find the success. So I could say down this subtree, right, in order to find this, I had to like cut off a whole bunch of branches, right? So based on how many branches I cut off, that tells me, well, was this hard to find or easy to find? And I'll reward appropriately.
Yeah, I think there's probably something similar there. I mean, I guess you don't want to punish if you happen to get lucky and the first thing you try actually is the right answer. Maybe you just got lucky. But you're probably right. Like if the first thing you try works, you probably should be suspicious, right? And it's maybe even just worth saying, well, sometimes some percentage of the time I'll get unlucky, but if I found an answer and I didn't do a whole lot of work, that probably means, I guess you can kind of look at this as sort of a sampling thing, right?
Yeah.
This reminds me a little of the Monte Carlo tree search type thing, where it's like we're exploring different answers and we're sort of getting confidence over time about how much we've explored the space of answers.
So does Monte Carlo tree search reward parts of the tree that are hard to get to but are successful? I don't understand enough about how it works.
Well, it can find, my understanding is it's good at like, if it can find an area where it can get answers, even if those answers are kind of expensive to get,
yeah,
that it's going to spend more and more of the time there. So it's going to sort of hone in on target-rich areas, even if they're kind of difficult to get to.
I wonder if, so when you've done some Monte Carlo tree search stuff, right?
I've mostly read about it. I've implemented a tiny little bit of stuff. Actually, I think Evan's done some stuff. But Evan, you've done some Monte Carlo, right?
Not really very directly.
Okay. You probably understand the theory better than I do, though.
Maybe a little bit, but I didn't get too far into that specific thing because I was working on something related at the time.
So if you were trying to do Monte Carlo tree search for miniKanren, weren't you like doing ProbKanren with somebody, Will?
Was
that Monte Carlo?
That was with Rob.
And is that Monte Carlo tree search?
It had some elements of Monte Carlo tree search.
Okay. So the key insight that I feel like I'm having is that if you're going to try and apply Monte Carlo tree search to miniKanren, you wouldn't just want, if it has some idea of what success means and success feeds back into it, liking that subtree, right? miniKanren has both kind of the tree of disjunctions and the tree of conjunctions, and they're kind of, layered on top of each other. And I suspect that Monte Carlo tree search probably only handles the tree of disjunctions and not the conjunction component, but I don't know. Do you have a sense? So, assuming that was true, then you would want to adapt the Monte Carlo tree search to recognize, the completion of conjunctions or conjuncts in a conjunction as a qualified success, right? That says, success was happening in this subtree.
Okay.
You may need to adapt that to, instead of it looking and only rewarding the things that succeed for the entire tree, reward things that succeed for subtrees as well.
Yeah. Well, I guess the model I have in mind, which is, it's not really Monte Carlo, but it's sort of like what Greg was doing for dKanren, where if a clause matches, you don't commit to it yet. You try the others to see if it's deterministic, if the overall thing is deterministic. And this feels similar to that. It's like, okay, if you find an expression that works, like, hold on, let's see if a bunch of expressions work.
Yeah.
Yeah, so maybe there is some notion of kind of how much work is required to get an answer, and you want to give preference maybe to those that are a little more expensive. I don't know.
Well, I'm not sure if I'm giving preference to those that are a little more expensive, but I don't want to. If an answer was really easy to get, I may not want to give it half of the remaining search time, right?
Yeah.
I may want to give it less instantaneous weight.
Sure. This is the other. This is also something where maybe a search where we can weight how much time each clause gets works well here, because if you trained on a bunch of scheme code, you might notice that the arguments to a recursion, well, a fair number of times are variable lookups, but a fair number of times are applications, something like that. Maybe it's 50-50. Right? You don't want either of those like completely dominating. Okay, well, I don't know if Greg's back or not, but yeah. We've got the fixed version of this interpreter, and basically, there's this make evaluate expo that's going to take context, just like the parent form, and then it's going to call out to the different ones. I guess the question is this the one to try to specialize, or do we do one before we got to this point where it was all inlined and stuff, but not dispatching?
I would start with that.
I think probably
sorry.
this one.
So, is there one that has the dispatching code but only dispatches to one?
I believe it's this one. Yeah. So it dispatches, but it always dispatches to the same one.
Yeah. So I would start here, because then we only have one case to worry about, and then you can copy and paste to the other ones later.
Yep. I guess I may as well fix it while we're waiting.
Indeed. Hi, Orchid.
Hey, Orchid. Just getting this all fixed up.
Seems like we should really do the Monte Carlo tree search thing at some point for real.
I agree. Oh. Whoops. Okay. I want to check my fixed thing, make sure I actually fixed it correctly. Oh, fixed code is not fixed. That looks fixed. Oh, yeah, it's supposed to be on A. That's right. All right. So, Orchid, we are trying to understand what's going on with the synthesis in terms of speed of things. Like, why is it hard or expensive to synthesize arguments of recursive function calls? And we think we have a theory here. You want to explain that, Michael, while I'm checking this in?
So the thought is we have an example where, say we're synthesizing a call to appendo, and we don't know anything about either of the two arguments. Sort of the naive interpreter without any of the Barliman optimizations, which is where we're starting with for this thinking, will start choosing pairs of values for those two things, and it will generally, like each of those, finding some value for each of those things will both succeed, and will only eventually fail when we hit the recursive appendo call, or sorry, recursive append call. So the idea is that, say there are dozens of different choices for the first thing, the first recursive argument. For each one of those, it's going to try infinitely many possible values for the second recursive argument. And because the way the search works, the more there are, each one ends up about having the time that anything subsequent receives, because of the way M+ is sort of set up. So that means that if we have an environment with 20 primitives, anything that is not a use of a environment-bound value, so choosing to do a lambda or something else there, is only going to get 1 over 2 to the 20th of the time, which is going to mean it takes a long time to try that possibility.
Okay, well, I've got everything fixed up, I think. So in particular, Orchid, I've got this example up. This example runs really, really slow. I'm trying to synthesize part of append. The two recursive subexpressions. And what seems to be happening is that the first variable u is hitting the variable lookup line, and it's trying to look up all the variables in the environment. And we've got a fair number of those because of the way we're handling the environment. We've got a bunch of primitives. And so once it decides that it's going to do a variable lookup, it sort of gets stuck there, and it's trying to do all these variable lookups, whereas there are infinitely many expressions v that we could pick before we do the recursive call. And in fact, u shouldn't be a variable lookup. It should be a call to cdr. So that call to cdr isn't really getting enough time to synthesize cdr vel, which is a pretty small expression, but still, this thing takes a very, very long time. Like, in fact, it hasn't come back unless you put some additional disequality constraints like this to keep the primitives out. So we're going to try to add Greg's optimization to application. In fact, I've got a version here. It's ready to go. Ready to modify this thing. So I guess here there's only currently one application. So it's a multi-argument lambda, right? Or multi-argument application. That was
multi-argument application is the case that we care about.
So it's right here.
Of non-primitives.
Yeah. And in fact, of non-primitives, okay.
All the primitive cases already work fine. So if you look at one of those primitive cases, notice that the eval listo happens after everything else, which means the input and the outputs are already connected.
Okay.
So here it's the problem that we have multiple recursive evaluations. We have the eval listo, and we also have the recursive evaluation of the body. So that last line.
For the multi-arg case.
Yep.
So for that one.
Yep.
Okay.
So we've got the rater, we've got the rands, and we've got the body.
Okay.
And the thing is, there is no optimal order of arguments, order of evaluation here. It all depends on the instantiatedness of different things. And so right now we're always doing the operands first, but we've shown that there's this bad case when we do that because we haven't hooked up with the output yet. So if we have the body of the function, then it can be beneficial to do that first.
Okay. All right, Greg, shall we fix up our multi-argument application? All right. So I've got some rather long file names. What's the maximum size for a OSX file name? Right. It's very common to do recursion on cdr, or with numbers recursion on n-1. Yeah, that's right, Orchid. I mean, I guess that's sort of what we're trying to get to with this code, so we can start trying some things like that. There are also a whole bunch of other things that we're not really trying that we could do, like if all the examples have exactly 2 arguments, then we could probably guess that they're 2 arguments, probably, right, to the function. Right now, that speeds up application to guess, if you instantiate that they're exactly 2 arguments. But if all of the examples that the person has given has exactly 2 arguments, then probably it's a pretty good guess. So there are little things like that we could do as well. I think Kent Divig considers that not an optimization, but rather not being stupid. So there are lots of places where it's stupid. Okay. Yep, exactly. In that case, if you're in an application, if you're an operand in an application, you're going to try cdr pretty quickly. That's coming early. But what we found, I think, is that this symbolo case could still cause you trouble. Is that right, Michael? Because that comes first, you could still get kind of stuck. In fact, that's exactly, we were using this version of the interpreter, so apparently that does happen in practice. Yep. That's right. That's right. And you could even have a little bit of a conversation with the programmer. You could have the paperclip. Clippy says, hey, it looks like you're defining a function with 2 arguments. Let me help you with that. Okay. All right, Greg. So what do I do first? Here are my rater and rand. In fact, okay. So the first thing I probably want to do is change the rater and rand so that the multi-arg is coming before variadic. Probably here too, because we don't normally do variadic, right? It's like not that common. Oops. Okay. First, it might be good to understand what a val application does. Okay. All right. So what does a val application do? It's very much a heuristic, not a perfect strategy, all right? Try ground arguments first, then the body, then fill in unbound arguments, any unbound final segments of the arguments. So those things, right? Okay. What does it mean, try ground arguments first? It's a misnomer. It really means anything partially instantiated. Okay. So, all right. Then the body, then fill in unbound arguments. All right, so Michael, can you explain why this would help with that case we were looking at, where we know it's slow?
So we're going to call the recursion, well, and I mean, this isn't necessarily ideal, but here the arguments are unknown, right? U and V are unknown.
Yep.
So we're going to start trying the recursion. So we're going to go into append, and so that means that we're going to go back and see the if null huh, right?
Yep. Yep.
And the s and the cons and car-l or whatever, right? So those are going to force properties of the expression that U evaluates to. Like, if we choose the null huh branch, then it had better evaluate to null. Or if we choose the cons branch, or sorry, the cons branch, then we do car-eval. So that means that U has to evaluate to a pair.
Okay.
So yeah, that's it.
So then when we're going to try to instantiate U, we're going to have those basically constraints on it?
Yep.
Okay, in that case, our variable lookups in the environments are going to be filtered out very quickly.
Yes. So really what would be nice, and I don't think even Barliman, well, Greg can tell me if Barliman's smart enough to do this. What would be nice is if we could go into append and evaluate append until we get to a recursive call and do things like, apply car-eval and all that kind of stuff, right? Because that would give us some information about U, like essentially its type. But then we could go back and be like, okay, well, it could be L or S, and we could try those. But I think as it is, it's just going to go all the way through append. So
you want to be able to stop it, like when you
Yeah,
hit the
it would be
recursive call
nicer-
again, stop it.
Yeah, it'd be nicer if maybe we could do that. But that's
Okay.
harder tech.
All right. Why is that harder?
Because you're having to more deeply reorder, right? So you're having to say, well, I want something now to happen in between two things that are would normally happen as part of the recursive call to append.
Okay.
So, the first part of the recursive call to append and the part where the recursive call makes a recursive call, right?
All right. So try the ground arguments first, then the body, then fill in unbound arguments. Any unbound final segment of arguments then gets tried with the eval listo. Okay. And so each one of these things is a goal, right, that you're building? Yep. Okay. All right. Well, this code looks kind of complicated. Lisp split ground implicitly projects. And the rest is analysis on the projected results. Okay. So Lisp split ground will need, is that relatively simple? Is it just going to split it into two lists of ground and not ground arguments or something like that? Oh, here's the split ground. Okay. All right, that looks like just regular miniKanren code. Yeah, this looks fine. The split ground looks fairly easy to understand. Okay. All right, so basically we're splitting the operand, so the operands into list of ground or not ground things. Is that right? So are R rands ground and rand suffix not ground, or not ground or something like that? I can't tell from those names which is which. And then, okay, goals, V goals, args suffix. Okay, so G goals is the ground arguments. V goals are unbound. List split ground does not look for whether an argument is ground. Okay, what does it do then? What it does is figure out what portion of the argument list structure itself is ground. Okay, I'm not sure I understand what that means. Is this just whether or not you have something fully uninstantiated, like a variable, versus something that has some structure, or is there more to it than that? For instance, when you say append dot comma x, where x is a logic variable, the argument list is completely unbound. True. Okay. So you could also have length instantiated, or you could have something where it's like xy.z, where it's a list of at least length 2. Whereas if you say append ab.c, then we know the argument list looks like, yep, lists ab.c. Okay, so the list of at least 2. In fact, it doesn't even technically need to be a proper list. So the first two pairs are known, and C is the unbound rand suffix. Okay. Now we're assuming for an application the lists are proper though, right? Yeah. Okay. So C has to be a proper list. We just don't know how long it is. It could be empty. All right. Okay. So what are RRANs and rand suffix then? So our RRAN. Yeah. So I guess I don't understand what list split ground does then. Like, what would we get back for lists? Would we get AB as RRANs and rand suffix be C or something? RRANs will contain BA, okay, so it's reversed. Rand suffix will be C, okay, that makes sense. All right, now RRANs means reversed rands, okay. Okay, so we have G goals, V goals, and arg suffix. So G goals, something ground. V goals, I don't know what V goals means. Virtual? Variable goals. Okay, so ground goals, variable goals, and then the body goal. All right, makes sense. All right, so we're going to take our RRANs and our rand suffix, and we're going to process those, it looks like. Well, we're going to process at least the RRANs, which we reverse. Okay, so now rands are just anything before rand suffix. Okay. Args is A star. So A star is the values. Those are the actual concrete values that are being passed in. Okay. So if rands is null, then we're done. So we're going to return ground goals starts out as succeed, V goals succeed, and args. Okay. Otherwise, let rand be the first operand. Okay. Let let / vars. Okay, I don't know what that is. Is that a racket thing, or is that something you made up? I don't know what let vars is. The A star represents what the rands evaluate to. Okay, sure. What is let / vars? So ST, I guess, is the state. Okay. Args rest. What is args rest? Let's vars. Let vars is like fresh for scheme level code. Lets you define new logic variables. Okay, so I guess we're defining args rest. ST is needed for let vars so that the vars get the current scope for faster MK's vars setting optimization. Okay. All right. So we're defining args rest to be a new fresh variable. Let goal be fresh arg. Now we're unifying args with arg.args rest. Okay. And then eval expo rand and arg. Okay, so we're creating this goal, which we're not running yet. And then if rand is a variable, if it's fresh, then we're going to do one thing, otherwise we're going to do something else. Okay, so we're going to loop. Each time we're cuttering down the rands, that's fine. I see. So we're going to decide whether or not to put rand on like, depending on whether rand's fresh variable or not, we're either going to build up the ground goals or the variable goals. So if it's a variable, we're going to basically just pass the ground goals back. And we're going to build up a new fresh. Ooh. So given what we learned last time, tracking through Orchid's issues, do all these nested freshes, are those going to cause problems with being left associative versus right associative? Is that going to be a problem? I'm not sure.
They look cleverly left associative to me.
Okay, good.
So see how V goals, the plural, comes first?
So if it went the other way around, it could be trouble.
That could be less good, yeah.
Okay. Less good. It's like my climbing partner used to say, falling outside is less good. V goals and then goal. All right. Okay. And then args rest. Otherwise, we're going to put it in the ground goal. Ground goals. Okay. All right. So we're going to end up at this loop runs with the ground goals, which is itself a goal, right? The variable goals. So basically, we're going to have a big conjunction of a bunch of ground goals, a big conjunction of a bunch of variable goals, and then args suffix. Why is it? Okay, args suffix. Args suffix is going to be args, okay. And args starts out a star, and then it's args rest. So where's args rest come in? Oh, that's that fresh thing. Okay. Args rest. Oh, wow. Okay, this is kind of weird code. This part's the weird part to me. Okay, so we're building up this goal right here. Yeah, this is the part of the code I find a little strange to read. The fact that we're passing in args rest here. And so we're not running this goal yet. So args rest is still fresh, but at some point args rest is going to be the suffix of args, basically, like the rest of args, when it gets run. So args. Okay, so we're kind of cuttering down. Okay, that's a kind of strange recursion pattern to me. Okay, we decide which bucket to put the goal in exactly. Okay, left associative is a good one. Args are gradually peeled off as we build goals for the ground portion of the argument list. Well, I feel like I've got a high level understanding of what's going on here, although I'd probably have to think about this part a little more. Can you, so we've got those args and we're peeling them off one at a time.
I've got to run, by the way.
Okay. All right. Well, thank you for joining.
Yep. See you later.
Okay. Okay, well, I've got some idea here. So as I understand it, so we're going to need list split ground, and that's just kind of a standard schemely thing. There's nothing special there. I guess we'll need let vars. A star represent values that the random value is to. Yes. Okay. Yep. I figured that part out. Here, let's see. So for this code, we're going to need let vars. Okay, so I assume that's some macro. And see, is there anything else that's tricky or that we need? So is that right? Do we just need list split ground and yeah, let vars? Okay, let me look at let vars real quick. I guess it's not defined here. It's defined somewhere else. It's an MK to SEM. All right. Okay, that looks pretty simple. Okay, nice. Okay, so that looks fine. That looks pretty easy to integrate. And then I guess the interesting part is that we're going to have to add it to the eval expert, right? And is it only used once or is it used twice? Yeah, it's used a couple places. 3 places. Right, you replace 2 lines with a call to the eval application. So, okay, so let's look at my interpreter here. So here is the multi-argument application line. So what would I replace in this case? Replace a call to eval listo and the final make eval expo. All right, those 2 are replaced. So so we're going to something like that. It's going to be here. Rather you pass the make eval expo goal as an argument. That's the body goal. Okay, instead of this eval expo thing, you mean? So this is going to be the make eval expo lambda multi or whatever. That. Okay. So let me use out. So this eval listo rand, does that get commented out? Or does this still happen first somehow? Oh no, that must get commented out, right? Okay. What about the extend end? Is that going to still happen? Do that before. So that's going to come up here. Like that. Body res val. Okay, so does that look correct? Okay. So now I just need the val application and all of its helpers, right? Let me try that. Okay. Okay. Okay, and we need this. And we need the miniKanren flippers. Okay, Orchid's a little confused about the problem though. Didn't you already generate append, or is this trying to do it with the language of LaTeX for the first time? Yeah, so basically, Orchid, what we're trying to do is see if we can take a simpler interpreter than the one that's in a Barliman that's been optimized a zillion ways, and see if we can try combining this n-gram approach with just the optimization, which seems to be the most important optimization probably for delaying or for reordering the goals or rescheduling the goals for procedure application. Because it seems like there were a whole bunch of improvements to performance that we got from the n-grams approach. However, n-grams approach still doesn't seem to work well for recursion. So recursive goals, or so like the arguments to recursion, sorry, that's what I meant to say. So if we're trying to synthesize append, there are lots of parts of append we can synthesize with just sort of the naive interpreter plus the reordering of the condes based on looking at scheme code without using any of the Barliman optimizations. It seems like there's lots of improvement we can get there, but we can't do well in the recursions. Don't seem to be able to do well there. So the idea is that maybe we can take, the n-gram approach where we reorder the conde clauses based on what patterns we see in actual human written scheme code, and combine it with one or two optimizations from Barliman, and have a fairly simple interpreter that actually performs really well. That's the hope, and that would make it easier to hack around and try to understand what improvements we get from the different optimizations and that kind of thing. Because I feel like we want to improve the interpreter by doing things like taking the n-grams approach and combining that with Barliman, but Barliman's current implementation is quite complicated. So we're trying to do something simpler that where we can do some experiments where we integrate different techniques. So that's the idea, or the hope. All right. So the question is, does this work? All right. Test one. Okay. With dummy. Okay, so test that. Application optimization. That's going. All right. Well, let's see if we can load this. Incorrect number of arguments to eval listo. Okay. Yeah, eval listo may have changed. Okay. Val listo looks pretty vanilla, actually. Expert and val. What's this one look like? Oh, okay. Of course, because it's taking the context now. That's why. That's why. So that all we have to do is give it the context, and it should be fine. Yeah. Right. So here, oh, I guess that means eval application needs to take the context as well. Oh, no. All right, let's see how we're going to pass this stuff around.
You shouldn't need to pass it to eval application because it's always going to be app ran star.
Oh, okay. All right, so we just need to pass app ran star into eval Listo.
And also into the eval expo that is called a few lines earlier on each rand.
Okay, so what was it? Was it ran star? Ran star, was that it?
Yep, that's right.
So we're going to do an app ran star there. And sorry, where were the other ones? We had calls to eval expo. Here we go.
Right
Here's
before the
one.
guard check. Yeah, there.
Okay, is that the only one? Okay. That should be it, right? Oh. Eval expo is not defined. That's true. The eval expo is not defined anymore. It doesn't exist.
Changed it to use the make eval expo thing.
Yeah. Okay. So rand 8. Let's go work. App ran star. Okay, that's right.
You're passing eval expo as the first argument to that mistake.
Oh, yep. Well, that looks like a good sign. It's actually running. Good, good. Okay, so now this is sort of a de-optimized version of the interpreter because, we're not, this actually has all the mechanism in place for the dispatch, but it's not actually using it. So what we want to do is now copy it over to the one that's actually doing it for real.
Also, due to the copy paste, there are several places where we'll need to call eval application.
Okay, is that something we can fix now?
In the dispatching versions of the interpreter.
Oh,
So
in the smart one, you mean?
Every time we're using multi-argument application, we have to make sure to use eval application.
Yeah, I agree. All right. Okay, so let's see if we can copy this over and get it right. So, okay, so here's the fixed. This is what we want. Okay, you're right. That actually wasn't that hard, was it? I was kind of shocked. Okay. So hopefully this will go well. All right. All right, we have a few of those. So this is the if, yeah, so this is the if one. All right. Now, is that right? Body res val, that looks right. So Greg, should I be able to run it now with just changing one of them?
I think any replacement should be semantically equivalent to the old version. So
Okay, so I should be able to test it now and do it one at a time.
yeah, I think so.
All right, I'll do that. Cool. Here we go. Okay. All right, that's nice. Let me go ahead and check this in as I'm moving along. Lazy. Okay. I think I'm ready to try the next one. So that worked. So I can add them one at a time. That's nice. Okay. All right, so this is the next one. methodical here. So presumably these are all the same, actually. I guess I can look for extend staro, probably. Yeah, here's one. Okay. Okay. Well, hopefully this will work. Not a copy and paste abstraction going on here. I think that's it. All right, I got them all. All right, let's try it. Well, it seemed pretty fast. Okay. Oh, I forgot to commit. Or, yeah. Oh, no, okay. What are those? Those are me. No, that's the wrong one. All right, that makes sense. All right. So let's try. It says it didn't come back. Let's try this one. Oh, nice. 62 milliseconds. Putting arity into the end. How would that work, Orchid? It wasn't coming back before. Yeah. Yep, that is definitely nice. Yeah, I mean, that's the thing, right? This optimization works really well with recursions. So let me try that. See if that comes. Nice. I like it. I like it. You got the whole recursive call. How about this? Wow. Wow. Oh, yeah. That is awesome. All right, what if I do that? That is so awesome. All right, let me put you there. Yeah, this is good stuff. I got all append in 0.6 seconds. Is that real? Let me hold on. I just gotta run that myself just to. Oh, it worked. Is this real life? Wow. I don't really need to put that in. I can just do this, right? Man, that is awesome. Oh, yeah. So, Greg, this even beats our current thing in Barliman, it seems. Yeah, so Evan, so there are two things. Like, okay, so basically this is a version of the interpreter that has two optimizations to it. One optimization to it is, well, okay, let me take a step back. If you look in the faster MK directory on GitHub, there's an interpreter called fullinterp.scm, which actually we found today, Greg pointed out, has an error in it. There should be some absento constraints on car and cdr to make sure they're not taking cars and cdrs of primitives. So we fixed that. There are also like kind of a couple of low-level optimizations, like just a little bit of hand reordering of things that look kind of dumb, I guess. But that's not really the reason we're getting good performance right now. The reason we're getting good performance is for twofold. One is we're using the improvement that Greg made for handling procedure application, where it's basically delaying goals and kind of dynamically reordering things to try to be a little smarter and trying to only run, basically trying to run code when you have ground values or partially instantiated values instead of fresh variables, so it doesn't have to guess as much. So we're trying to avoid generating tests. And the other optimization is the sort of bigram, ngram stuff I was messing with, where the condy clauses are being reordered based on the context of how things are being used. So like if you're inside of a lambda, the thing that you're going to try is probably an if or something like that. It's going to be more likely than in some other context. But if you're trying, if you have a cons, the argument to a cons is probably less likely to be an if. So those are the two optimizations we're trying. And at least for append, they seem to work quite well. This is beating Barliman in performance, I think, or certainly as fast as Barliman for this particular example. Now, maybe it doesn't work well for other examples. I don't know. But the cool thing about this is I think there's some other there's additional context we can give. This was just basically something I hacked together in one night as far as the context part. So that's why I'm optimistic that we can push this further. And of course, we're not, there are other things, other optimizations we can do. So what's after append? I'm not sure I understand that question. Oh, as a benchmark, yeah. Good question. Well, let's see if we can synthesize some code with, well, okay, so one thing we can do is we can try some of the benchmarks from Barliman. I know Greg's got some of those. Greg, can you point me to those? Synthesize Barliman and Barliman. That's right. No one's leaving until we can do that. Okay, first of all, before we run other benchmarks, I just want to get this test. checked in. Because that's cool. That's really cool. So I just texted Michael. You missed the punchline. Okay. Anyway. Oh. It's annoying. Oh yeah, I gotta say what the output is. Duh. Nice. Okay. All right. So that's pretty cool. So let me check that test in. Okay. So Greg, well, okay. I guess the other thing, we do have some tests here for, what else? I had map tests, right? Yeah, I commented all these map tests because they were like super slow. So maybe it's time to uncomment those tests. Do it. Yes, right. All right. Some of these tests were quite slow indeed. In fact, this one was like quite bad. Let's try it again. Map 1's still kind of slow. What's map 1 doing? Oh, it's trying to guess symbol. Huh. Well, that's not so good. Well, map 1 doesn't seem to be a winner. What else we got? Map 19. Map 18. Okay. Let's try some of these synthesis examples where we're. So there are a couple of modes. Like you can either try to synthesize map, or you could try to synthesize like what you're passing into map. Okay. 8 seconds. Let's see. It's not so good. Now this one probably depends a lot on the tests and things like that. I also wonder if that's partly the test, Greg, because the tests probably are kind of significant. Yeah, maybe there are cases where things like splitting the environment makes it faster. There's other optimizations. Yeah, it's pretty slow. So that's an interesting question. So what is it about map that's different from append? And is it just, I happen to use really efficient tests? I don't know. But this one's not looking so great. All right. Well, we could try. We could try against some of the Barliman tests, I guess. There is a map one, right? Oh, I'm not using my gensims. I wonder if that makes it okay. Well, let's take one of these maps from. I don't know that. Does that even run? It failed, so something's not right. Something's not right. I guess I can't just take the test from Barliman necessarily. Oh, because it doesn't know about begin, of course. So this is going to be, we're going to have to redefine it. I guess we have to do something like let rec. Rec map, and I'll call this code, I guess. Let's see if that works. That looks right. Is that right? Lambda fx, if null. Huh. Well, maybe it was the gensimming that was the problem. That may have been the null test. Okay. Yeah, because it looks like it's all ground. Okay, fine. Good call. All right. Well, let's try this one, I guess. Oh wait, let's see. I don't know what's a good test. Is there one you would suggest, Greg, that Barliman can do okay on? Anything uncommon that Barliman can do. Okay, so map A. So what is this about? This is That's just trying to guess f. Is that all that's doing? Hard2 figures out what to pass to map recursively. It was pretty hard at one point. Okay, well, let's try that. So let's have a fresh f, I guess. And I think it's this one, right? So it figured that one out. Okay. Let's wait, is there a harder one? So this is commented out, so I don't know what that means. Did you look at hard one? Is it this one, hard one? Oh, I see. Okay, so we got A, B, and C. All right, let me try that. That's F. We got A, B, and C. Okay. So we want to put an A in the base case. Okay, you can get that. We want to put a B. It's the first argument to cons. Ooh, that looks tricky. All right, got it though. And we want C to be the cdr of excess. That looks like the hard one. Oh! Okay. Okay. So do you know, Greg, how well a hard one does?
What are you waiting for, by the way?
I was just texting Michael. Okay, so what? So let's see. So we want to do.
So there's a hard 3 and a hard 4, by the way, that Barliman
Yeah.
review. They're just a bit slow. Maybe
Okay.
about a minute each.
So here, what? Just
the entire body of map. And hard 4, I think, doesn't even give it the argument list.
Okay. So let's. I mean, do you know how long it takes?
I think it takes about a minute, but it also make sure you're using the right test cases. I think
Okay. Are they different test cases?
Maybe they're the same. Never mind.
Well, you're right about the test cases probably being important. So let me add these to the tests. Yeah, so I guess the problem is the tests I was using for map aren't really using the GenSim stuff. It just makes it way harder. Okay. So yeah, so let's do hard 3, I guess. All right, so lambda FSA. And let's just double check those tests. Do less car, coder, campus. Those all look okay to me. Okay, it may take about a minute each, 15 to 30 seconds. All right, well, let's see if this works. I think that's it. What happens? Whoa. Whoa, it came back right away. What happened? Bang! Whoa! Whoa! I shall wrap the run or whatever. Let me do that. Okay, so that's 3. And let's do 4. Okay, so for 4, that's what? Just like no structure at all? Okay, so basically I can just get rid of the code thing at all, like that, I think, right? That should be, I think that's equivalent. All right, well, we'll see how long 4 takes, but 3 was pretty good, huh? So the LUTREC is going to have a lambda on the right-hand side. So I guess the only thing is that, we have this problem where if it doesn't know how many arguments it's going to take, that really slows it down a lot. I think that's what we're testing here, is the effect of not knowing how many arguments, which seems to be considerable. Yeah, guessing the argument list and doing a bad job. That's right. Well, Orchid, so do you had an idea, or whoa, okay, so it finally came back. How long did it take? It took 95 seconds. Yep, it looks like it's right. And I suspect that if we do like a 3B and we make the we make it list instantiated, length instantiated, I mean. 7 seconds. That's interesting. Did you see that, Greg? It's just even knowing the length, but not having concrete variable names. Yeah, it's like 3 times longer if you don't know the variable names. Okay. Same length. What is this for? This is enforcing something about lengths of the argument lists and the operands lists. Is that what that's doing? Okay. So far it seems either on par or faster than Barliman for those 2 examples at least. We should, yeah. Yeah, okay, sure. So why do you think it's so much slower when it doesn't know the variable name? Is that more environment lookup somehow? Or maybe it doesn't know that the 2 variables aren't the same. Oh, that's an interesting question. Let me try this. I've got an idea. All right, so same time, over 7 seconds. Now what happens if I say X and Y are different? Does that speed it up? Nope, about the same. All right, yeah, I'm not sure why it's so much slower when the variable names aren't concrete. Other than, yeah, let's see. Or F and, well, that's for whatever we want. That's, I guess. It's way faster. Way faster. Oh, yeah, it could be shadowing. Well, that's interesting. So it does seem to make, at least in this version, makes a lot of difference if you give it a concrete name. I don't remember seeing quite that big an effect in Barliman. Yeah. Okay. Well, all right. Well, I tell you what. I mean, we've gone on for quite a while now, and just out of respect for people's time, I guess maybe we should call this a success, and then I'll do my laundry and get some food. But it actually worked. What were we saying, Greg?
Sounds good to me.
Yeah, that worked better than I thought it would, actually. So do you think that the environment optimization would also have a big effect?
I think that would help reduce that 96-second time significantly.
Okay. But the 96-second time wasn't completely out of whack with what Barliman's doing right now?
No, the Barliman one was already between 70 and 90 seconds before, but that was the last time I tested that was before I tried the argument length quality.
Okay. So there are a few other optimizations we could add. I mean, I have to say that this didn't seem to make the code any less clean, really. I mean, it's nice that you could just kind of drop this in. You know, we didn't have to like go through and modify all the code.
Right. The other really interesting benchmark that we were able to do with some of the other optimizations was the sort of property-based equality test cases being used to synthesize append. Yeah. Okay. We may still have trouble in this interpreter doing that.
Sure. Well, if nothing else, this also makes me think that we should. Okay, so I guess the other thing we should test is this version of the interpreter. Or sorry, we should test the naive version of the interpreter. Or yeah. No, we already did. We already did, right? We already tested the interpreter that isn't actually taking advantage of the reordering, and that actually wasn't that fast.
Right.
So we are definitely getting a benefit from the combination of the application goal reordering or whatever, and the sort of optimizing the Kandi order a little bit.
Yeah, the context sensitivity really helps here, I think.
Yeah, so I think that is worth pushing and trying to figure out how we could implement that in Barliman or whatever.
Yeah.
Alrighty, everyone, I'm gonna take off. I gotta go. I gotta hit the bathroom. I will see you all not this coming weekend, but the weekend afterwards. Yeah, thanks, Argid. That was fun. Yeah, so next weekend I'm going to be in North Carolina, but after that I'll be back. So if you all want to do a hangout, feel free. If you want to play around with this code's all on GitHub. I just put it in the miniKanren Hangouts, GitHub repo. Yeah, woohoo! I'll finally get to meet Evan. That'll be neat. We can do Monte Carlo tree search. Yeah. But anyway, that was actually cool that we were able to pull it together in one setting, and this makes me think that as we combine more and more of these features, we should be able to do pretty well, I think. Yeah, so 0.6 seconds for append. That's not too shabby, given that we're not using types or anything. And I think we can get more effect from the context as well. I think we're using context in kind of a naive way. It's just like it's just much better than not using it at all. So we did get a big improvement there. Yeah, that'd be awesome. All right, everyone. Thanks for joining or following along. Take a look at the code. Try to play around with it. That was actually cool to get this relatively simple relational interpreter doing synthesis pretty well. This I actually can understand. Like I can imagine explaining this interpreter to someone in a miniKanren hangout or something like that. Whereas with full Barliman, I don't understand all the bells and whistles yet. But hopefully we'll add those one at a time or something like that. Okay, talk to y'all later. Bye.